India's Chandrayaan-3 mission has already secured its place in history. It put India in the select group of countries that have managed to land on the moon, the fourth on the list, and it was the first to touch down in the lunar south polar region. The landing of the Vikram module, with the small Pragyan rover on board, led to discoveries that helped decode the chemical makeup and geological history of our satellite. It also delivered valuable data for anyone planning to return and stay there longer. Yet amid so many successes, the most intriguing part wasn't what the mission found, but what it didn't find, something everyone expected to see. Let's revisit this Indian mission and find out what India saw on the moon. Even before launch, ISRO, India's space agency, made one core objective clear: to search for signs of frozen water. That was one of the main reasons for choosing the South Pole as the destination. This region contains craters that never receive direct sunlight and act as true thermal traps, ideally suited, in theory, to preserve ice for millions of years. If we want to dream of permanent bases, we need to understand that water, measure where it is, and in what quantity. The question hanging in the air is straightforward: where is all that water? This hunt didn't start now. Back then, it was also India's Chandrayaan-1 mission that helped strengthen the evidence for ice in the polar craters. The idea of water on the moon has been around since the 1960s, and in 1971, Apollo 14 detected traces of water vapor at the surface. But actual ice, water in solid form, was slippery to confirm. The most promising hypothesis pointed to the polar regions. There, the terrain's geometry leaves parts in eternal shadow, with some of the lowest temperatures in the solar system, the perfect place for ice to form and persist. The problem was that images of these areas were, for a long time, too dark, low resolution, or inconclusive. We detected hydrogen spread across the surface, but we couldn't assert that it was bound to oxygen as frozen H2O. In 2009, a crucial advance arrived. Chandrayaan-1, equipped with NASA's Moon Mineralogy Mapper instrument, found definitive spectroscopic signatures of ice in dozens of craters near the poles. Later, Chandrayaan-2 confirmed this hydration map. Confidence grew among scientists that there could be something like 600 million tons of water ice in permanently shadowed craters. That's a lot, and it's easy to see why that's exciting. To establish a human presence on the moon, hauling water from Earth would be extremely expensive. Finding water there would allow drinking, growing plants, recycling, producing breathable oxygen, and even splitting the molecule to obtain hydrogen and oxygen, useful ingredients for rocket fuel. In other words, water is life, air, and mobility. With that backdrop, Chandrayaan-3 launched on July 14, 2023. The architecture was simple and efficient. A lander, Vikram, a compact rover, Pragyan, and an orbital module that carried both to lunar orbit. On August 23rd, at the start of a lunar day, Vikram touched down with Pragyan stowed inside. The timing mattered. A lunar day lasts about 14 Earth days. After that period, night falls, and the temperature plunges to around -120 degrees Celsius. Because the project was designed to fit a tight budget, the lander and rover didn't have heaters and batteries designed to survive the extreme cold of the night. In fact, the cost comparison made headlines. While a launch in NASA's Artemis program has an average estimated cost of $4.1 billion, all of Chandrayaan-3 cost about 6.15 billion rupees, roughly $75 million. Ironically, less than many sci-fi movies spend to go to the moon without leaving a studio. That budget trimming required technical choices, including accepting that the mission would have a short window to meet its goals. So, as soon as Vikram opened the ramp, Pragyan rolled down and got to work. Pragyan weighs 27 kilograms, has 6 wheels, and 2 main scientific instruments. The first is APXS, an alpha particle X-ray spectrometer that bombards material with radiation and reads the return to identify chemical elements. The second is LIBS, laser-induced breakdown. Spectroscopy. The laser vaporizes a microscopic spot on the target, and, from the light emitted by the plasma, the composition is identified. Together, they're a powerful combo for sniffing the soil and looking for signals of interest, including water clues. With the instruments positioned, the rover began measurements right next to the landing site. The first results painted an encouraging chemical portrait. Aluminum, calcium, iron, chromium, and titanium showed up in the samples. Oxygen was detected too. From a scientific standpoint, there was a historic first, the first in situ measurement of sulfur in the Moon's polar region. Sulfur is important for understanding how the Moon evolved geologically and suggests that the area had volcanic activity in the past. However, one key element wasn't there: no indication of hydrogen in the rover's measurements. Without hydrogen, there's no detectable water in the surface soil examined. The frustration was understandable. If there's ice nearby, why didn't Pragyan see it? Meanwhile, driving the little robot required a steady hand. Control was manual, performed by the team on Earth using images from the navigation camera. There's a communication delay, just under 3 seconds between sending a command and seeing the effect. That sounds small, but for a vehicle that must avoid slopes, rocks, and crater rims, it's an eternity. Right at the start, there was a scare. Operators had to command an emergency stop to avoid plunging into a 4-meter crater that hadn't been noticed at first. Emergency is a figure of speech here, since Pragyan's cruising speed is about 1 centimeter per second. Over its entire lifetime, it traveled roughly 100 meters from Vikram. Elsewhere along the route, it again skirted a depression, probably another crater. There are no photos of this second obstacle, and there was no report of visible ice on the edges. If anything was gleaming there, it wasn't recorded. Vikram, for its part, didn't sit still. The lander used a sensor called CHAR-STE to measure how temperature varies in the soil. The probe inserted the instrument down to 10 centimeters in depth in 1 centimeter steps, recording how heat behaves in the shallow layers of regolith. The lander also assessed the tenuous plasma above the surface. Good news, there's little ionized material there, which indicates that radio transmissions to and from the Moon are likely to suffer little local atmospheric interference. At another moment, the seismometer detected a possible moonquake, a lucky break in such a short operational window. As if that weren't enough, at the end of the campaign, engineers tried an extra experiment. They gently fired Vikram's thrusters to make a hop of about 40 centimeters in height, shifting it 30 to 40 centimeters forward. It sounds small, but it demonstrates in miniature the idea that future landers could make small adjustments or even lift off back to orbit after landing. Despite the volume and quality of the data, one piece was missing. The ice didn't show up. On September 4th, as lunar night fell, the mission prepared for the end. Vikram and Pragyan were put into hibernation mode, oriented so that they might perhaps wake up at the next dawn. The ISRO team hoped they would, but knew it would be difficult. In the end, the cold won. Both failed to wake and fell silent for good, ending a short and successful journey. India celebrated, and so did the scientific community. It was 2 intense weeks with unprecedented information, especially about conditions at the South Pole. Even so, the question remains: if ice was mapped from orbit, why don't we see it on the ground? Here's where a counterintuitive part of the story comes in. When we hear ice on the Moon, it's easy to picture white sheets on dark ground or fields of crystals like frozen stalactites. Maybe a frost coating the soil of craters in constant twilight. When ShadowCam, an ultra-sensitive NASA camera aboard South Korea's Danuri probe, began sending images of permanently shadowed craters, many people thought they'd see those glittering carpets of ice. And once again, nothing, just dust, barren terrain, deep shadows. Beautiful, intriguing, but without the expected white layer. The contrast between orbital spectroscopic detections and the lack of icy landscapes in photos and in situ measurements creates this uncomfortable mystery. If Pragyan didn't see water molecules in the surface, regolith and ShadowCam didn't catch glints of exposed ice, where is the stockpile that orbital instruments indicate? The answer may lie in the numbers Vikram measured with CHAR-STE. The temperature readings showed something revealing. Near the surface, during the illuminated period, ground temperatures stayed just below 60 degrees Celsius, warm enough to make any exposed ice unstable. However, as the sensor pushed downward, the heat dropped quickly. At just 8 centimeters deep, the temperature fell to about -10 degrees Celsius. In practical terms, that reveals 2 things. First, lunar regolith is a poor conductor of heat. meaning it insulates the inner layers very well from the brutal day-night swings at the surface. Second, if ice exists, the likeliest place is tucked beneath the first skin, shielded from the sun, in pores and grains of the soil, or in microscopic pockets and thin layers just a few centimeters down. This interpretation reconciles several facts. Orbital detections don't necessarily see a sheet of pure ice out in the open. They may be picking up hydration signatures, ice mixed into the regolith, perhaps as films and microdeposits spread across the terrain. At the same time, if the surface heats to 60 degrees Celsius in the lunar day, any naked ice would tend to sublimate, jump straight from solid to gas, and gradually be lost. Below, however, the sub-zero temperatures create a natural vault. Think of the soil as a thick blanket. On top it warms. A few centimeters down, it's a freezer. That's why the practical advice emerging from Chandrayaan-3 sounds almost prosaic. If you want to find water on the moon, bring a shovel. Of course, that opens other research fronts. How much water actually exists under these conditions? Is it concentrated in specific spots or distributed like an extremely low concentration humidity? How does this water move over the day-night cycle? Do the solar wind and the sun's ultraviolet radiation influence this balance, breaking molecules and shifting hydrogen across the surface? Is there constant resupply from volatile-rich micrometeorites or from processes inside the moon itself? None of that is fully explained. But Chandrayaan-3 added an essential piece, a real thermal profile of the soil in that region, measured in the field, showing that the boundary between the heat that expels ice and the cold that preserves it lies just a few centimeters down. Looking at the mission as a whole, it's easy to see why it's so celebrated. On a lean budget, India carried out the first landing at the South Pole, operated a rover with instruments capable of sniffing the local chemistry, measured the plasma environment, recorded a tremor, performed a micro-hop, and brought to light a puzzle that will guide next steps. Pragyan didn't see hydrogen in the surface samples it analyzed, which reinforces the hypothesis that the ice isn't out in the open, but stored just below. Vikram, with its temperature measurements, pointed exactly to that shallow depth where the day's heat no longer dominates. Some people feel a twinge of disappointment that we don't have photos of ice chambers gleaming in the dark. But science rarely delivers the postcards our imagination creates. In return, it gives us tools to work with reality. The picture now is of a moon with water, yes, just in a less cinematic and more challenging form. Ice mixed with dust, trapped in grains and cracks, hidden from the sun just centimeters below the surface. That calls for more refined prospecting, drilling, and extraction techniques. But it also points to a clear path. With probes and rovers that dig a little deeper, sensors tuned to pick up subtle signals, and missions that combine high-resolution orbital maps with in-situ measurements, we'll turn that maybe into a reliable inventory. Chandrayaan-3 lived only 2 lunar weeks, which was certainly less than the team had hoped, but enough to refocus the whole community. If we want to drink a glass of water at the lunar South Pole, looking for a frozen lake probably won't cut it. We'll need to take on the patient work of digging, sieving, and heating samples to release and capture what's there, quietly waiting for millions of years. And that, let's be honest, is excellent news for anyone who dreams of building something lasting up there. Buried ice is a stable resource, protected from extreme temperature swings and solar bombardment. Once identified and accessed, it can sustain bases, refuel spacecraft, and open the door to a real, continuous human presence. In the end, the mission not only delivered what it promised, but also sharpened the right question. It's not, is there ice on the moon? But, where exactly is it? At what depth and in what form? The answer is starting to appear, not on the heated surface, but just below it, where the cold rules. India showed that it's possible to arrive, land, measure, and learn with admirable efficiency. The next visits, from India itself and from other agencies, will dig into that idea, literally. Until then, if someone asks for practical advice on finding water on the moon, it fits in one simple, down-to-earth line: start by bringing a shovel. Give the video a like, subscribe, and share. Thank you for watching, and see you in the next one.